Hello, everyone. My name is Rich Ottinger, and I am the Marketing Programs Manager for Park Systems, coming to you today from Albany, New York. Welcome to today's webinar, Electrochemical AFM, Copper Deposition, Dissolution on Gold. Before we begin, let me give you a quick overview of today's session. The presentation will last approximately 25 minutes, after which we will have time for a short Q&A session. Please enter your questions at any time into the questions module of GoToWebinar. If you prefer, at the end of the presentation, you may click the raise your hand button and I will unmute your line so you can ask your question. It is now my pleasure to introduce to you Dr. Jiali Zhang. Please welcome Jiali.
Okay, thank you for the introduction. Hello, everyone. Good morning, good afternoon, and good evening, depending on where you are. My name is Jiali, and I'm the Technical Service Engineer here at Park System. And it's my great pleasure to give the short presentation about electrochemical atomic force microscopy for copper deposition and dissolution on gold experiments. So before we get started, and I want to give you a brief introduction about our company, Park Systems. Park Systems is a world-leading manufacturer of atomic force microscope and emerging nanoscale microscopy systems. We develop solutions for many research and industry applications, enable advance in science for major universities and national labs and a variety of national companies specialized in diverse fields. So our product line covers just about every usage case with fully manual to fully automatic AFM systems. As you can see here, we have our research product line from XE7 system, which is the most economic choice for research AFM, and to our Park NX high-back. So, and also we provide you with fully automatized industry system from HDM and X3DM for wafer characterization purposes. In general, our AFM technology offers the best accuracy, the highest resolution, and it is the easiest to use on market. So if you want to learn more, please visit parksystem.com for more information. So before we get to the actual experiment results, I want to briefly talk about the principle of EC-AFM and what do we need EC-AFM for. So EC-AFM, it was developed in 1991 on the base of AFM, and so therefore it extends AFM technology to the field of electrochemistry for study of the solid-liquid interface reaction by allowing in situ AFM measurement during EC reactions. So the basic working principle of EC-AFM is very similar to that of AFM and shares the key components. So we have a sharp tip and XYZ scanner and feedback control systems as shown in the diagram of a typical EC-AFM. In addition, EC-AFM requires an EC cell that can accommodate the working electrode, which is usually the sample, and the counter electrode and reference electrode, as well as a potentiostat that controls the applied potential of the sample that controls the interfacial reactions. And during the scanning, the sample is placed in here, and as a working electrode and the EC reaction is happening here. And then by scanning the tip, the force between the tip and sample is measured by monitoring the fraction of the cantilever to obtain the topography or morphology changes of the sample during EC reactions. So typically before AFM measurement, a cyclic voltammetry or CV curve is employed to investigate or control the reduction and the oxidation process of molecular species. So what is the CV curve? So the CV curve is a curve for the current versus potential for a linear potential sweep. So here shows you a typical dog-shaped voltammogram. X-axis is the applied potential, while Y-axis is the resulting current that passed. So for example, when a solution of Fc plus is scanned to a lower potentials, and it will reduce to Fc locally at the electrode. That's resulting in the measurement in current and depletion of the Sc plus ions at the electrode surface. Then when the switch potential reached, the scan direction will reverse and the potential is scanned to a more higher potential, and the Fc on the electrode surface is then oxidized back to Fc plus as the applied potential become higher and more positive. So with the understanding of the CV curve and then by using EC-AFM with a potentiostat, one then can monitor and control the morphology change on the electrode surface. And for applications such as electrochemical induced surface reconstruction and or some metal corrosions or corrosion protection, as well as determine the performance of batteries. So EC-AFM option is available in all Park research tools such as NX10, NX12, or XC series. In today's sessions, the experiments were mainly done on an NX12 systems, as shown in this picture here. The advantage of NX12 is that it couples Park AFM with a sample stage for inverted optical microscope so that you can see through the transparent samples. So to perform an EC experiment, as I mentioned in the previous diagram, the EC cell is needed. So our Park NX EC cell is specially designed for EC applications. The cell is made of polychloro trifluoroethane, so that guarantees the chemical stabilities. So a variety of solutions can be used here. And it also provides 4 electrode leads at the top side of the sample and 1 at the bottom side. And it can be easily mounted on Park AFM sample holder. So here shows you the overall structure and the individual components of the previous NX EC cell. So the sample or the working electrode is mounted with top cover and sealed with a thin silicone O-ring that securely prevent leaks to the back side of sample. On the right side, this is electrode diagrams. You can use platinum iridium wire as a counter electrode and silver chloride as a reference electrode. They are all supplied in Park's EC-AFM starter kit, but any customized electrode can be connected to an electrode lead. So this is our true experiment conditions for today's copper deposition and dissolutions using EC-AFM. In the experiments, we use a liquid probe head. So for AFM image in liquid, it is made of peak material. Therefore, its resistance to most buffer solutions include acid and base. So the solution we use will be copper sulfate to provide copper ions, and the working electrode will be gold thin film on mica. And this is a counter electrode and a reference electrode. For potentiostats, we use this model. However, any working potentiostat in your lab would be fine. So then we will connect the cables between the potentiostat and the EC cells based on the diagram shown here. So this is the actual setup in our NX12 sample truck. So this is the EC cell with connections cables. And so in the EC-AFM, the working electrode is the sample surface. So is where you monitor the EC reactions. While the working electrode area is bigger, the counter electrode area, signal saturation will occur. Therefore, normally we will make the counter electrode area wider, like showing here. So before we move to the AFM results, we have to sweep the potential and generate the CV curve of this redox reaction to find out the right potential to control the deposition or dissolution of copper. So as we mentioned, by sweep the potential back and forth, a reversible CV curve will be generated after successful setup. So as showing here, this sweep was steady run for 10 cycles, and you will see the overlapping is pretty well, so it means the reaction is reversible. And based on the CV curve generated here as a potential that scan more positive from A to D, the oxidation happens and the copper dissolution occurred while switching back from D to A. The reduction happens and then the copper deposition will occur on the working electrode. So now I'm going to show you the video of the EC cell during the CV curve generation. At the beginning, the oxidation reaction happens and copper ions is reduced into copper and deposited on the working electrode, and that shows this brownish color. And then by sweeping back to the negative potentials, copper dissolved and it's oxide back into copper ions, and the gold surface is appeared. And then by keep sweeping from negative potential to positive potentials, copper deposition reoccurred. Therefore, you can see the brown colors shows again, and then cover the whole working electrode area. So now we can switch to the actual AFM result. This is a bare gold surface with visible terrace image with by AFM in liquid before NSCV sweep. Then based on our CV curve generated just now, one can find the threshold potential for copper depositions, and then we will apply negative 0.6 volts continuously. And after that, we will take the AFM image of the same area. And you can see this AFM image by scanning from top to down. With the time increase, the deposit copper cluster grow from smaller size to bigger size. So this means that the deposition rate is increased with time. So using the same imaging as example and back to the CV curve, if we choose to apply a more positive potentials, like in here, by applying 3 volts, and then after that, we're taking the image of the same area, we'll see that the deposit copper clusters were completely removed, and the bare gold surface is exposed again. So by comparing these 3 images together, you can see that the same area of gold was the gold domain was remain the same by comparing A and C. So you can see the hole here, and then these domain features are exactly the same. So that tells us the reaction is fully reversible. So the in situ dissolution of copper is also monitored with AFM, an example showing here. So while scanning from the top to down, in the middle of the image, we apply the positive 3 volts, and right in front of this horizontal green dashed lines, and you will see that the high domain of copper island will decreasing in here and completely dissolved, and that's the bare gold surface is regenerated again. So this is shown in our AFM image. You can see the trends as well as shown in our cursors that 75 copper domains was decreased and dissolved completely. So and also you can change the parameters, such as change the working electrodes to platinum surface, and with a more diluted surface, use a more diluted solutions, and by reproduce these EC-AFM reactions. And you can monitor the real-time copper redox reaction in our built-in optical microscope. Here, the examples before reaction, the platinum surface is black, and then the platinum surface AFM image is also shown here. And then after the reduction, the brownish copper color is shown in the optical views, and also the domains of copper, small domains, and it shows in the AFM images. And by doing the oxidation reaction, you will find that the brownish covered area is diminished and becomes smaller, so as copper domains is decreased in this AFM image. So the optical views of our built-in optical microscope give you the microscopic evidence, and the AFM gives you the nanoscale evidence of this redox reaction is happening. So with that, I want to get to our conclusion remark, and In this study, we made an electrochemical system in AFM with CV measurements for in situ observation of the electrochemical reaction. We observed copper deposition and dissolution process during CV measurements with EC-AFM, and also obtained in situ image of the surface morphology. This AFM showed the in situ morphology changes during electrodissolution of copper. And Park Electrochemical AFM package is designed for wide chemical solvents and which enable long-term in situ electrode study using under EC control and in different solvents. So with that, I want to thank you for your time, and I'm really happy to answer any questions and if you have any. So that's it.
All right, thank you, Jiali. And we do have one question so far. If anybody else has a question, please feel free to enter it in the questions module or click on the raise your hand button and I will call on you shortly. The question that we got so far is, what's the supporting electrolyte?
Supporting electrolyte, you mean the working electrodes? We are using the gold surface, but you can use any conductive surface like platinum in the second experiment.
Okay, anybody else have any questions out there? I don't see. All right, so the same questioner is saying, what is the solution? I think it's just a question of whether this is a liquid or not.
Okay,
experiment.
So the electrode solution is copper sulfate. And you can, of course, use other redox reaction species and then do it, because we use it so we can easily see the deposition of copper on the surface.
All right. Give everybody just one more second here to see if they have a question or wanted to raise their hand. All right. I don't see anything coming in, so I will move towards wrapping up the session, but feel free to continue to enter questions. If I don't get to it before we finish, we can always answer you in a follow-up email to the group. So thank you, Jiali, for the presentation. Oh, we do have a couple questions coming in now, so I guess we'll go back to that. So the scanning is done after the reduction or oxidation reaction?
So we show that this one was scanning done after the reactions, but in this experiment, scanning was done during during the reactions. So that's why you can see the copper domains at the beginning and diminished in here and completely dissolved, and that's the bottom gold was exposed. Of course, you can apply negative potentials and see the backwards reactions happens.
All right. And that's the same question. So I think that you answered that one already. All right. So thank you very much for your presentation, Jiali. The next webinar in this series is scheduled for June 24th, once again at noon Eastern Time, on the topic of nanolithography. We will also be holding the next session of our live demo and chat series this coming Friday at 3 p.m. Eastern Time. So please consider joining us for that and visit parksystems.com/online nanoacademy to find info and register for all of our online offerings. One more question, I guess, came in. I will pose to you before I finalize the session. How does the probe that reads on the working electrode work?
The probe, you can use some of the probe that have a Teflon coating at the back. Therefore, those electro signals will not interface during the AFM image. But for today, this experiment, I use a normal contact probes and it works just fine. Maybe you need to control the reaction rate as well as electrode solution concentration so that you can have time to to see this in situ morphology changes by slowing down the reaction rate.
And what was the scanning mode?
So it's contact mode.
All right, I think that will do it. So thank you all again for joining us for this session. You can find more information about Park Systems AFM at parksystems.com, and please direct any AFM questions you have to inquiry@parksystems.com. If you have any questions specific to this webinar series or this session, feel free to reach out to me directly at richard@parksystems.com. Thank you. Have a good day.
Thank you.